YouTube. Testing on YouTube. I got an ad on my own stream. Great. Testing on YouTube. All right, YouTube works. Let's do the last one. Testing on X. Testing on X. All right. We're live on X as well. All of the streams are working. Let's go ahead and announce the beginning of the stream. How's it going, Sarah? How's it going, Jamal Boussouf? And Isaac? Welcome to another Hoopo stream. Hope the lack of a stream last week didn't put you guys in too bad of a situation, but today's stream is going to be called Visual Reasoning. We got a whole bunch of papers for this one. Almost like 6, 7 different papers. And I'm trying something a little bit new here, so I really have to recommend this thing that I discovered. It's called Illuminate from Google. It feels like the Notebook LM, so my guess is that it's the same team, and now this is like the upgraded version of their product. But you basically put in the URL for an archive paper, and this feature here, which I think is the greatest upgrade over Notebook LM, is that you can ask it to make a podcast, except a more technical expert podcast, right? One thing that I found with Notebook LM that was kind of annoying is that the podcast was a little bit too casual. It kind of didn't feel like I was actually learning, but they fixed that with this feature here. And all of the papers that I'm going to be reading for this stream, I also shared a link for the Illuminate podcast. So if you want to hear 2 AIs talk about it, you can listen to those. Those are in the doc links. How's it going, NLP prompter? That's a long breath. Yeah, I've been kind of trying to get good at circular breathing. So circular breathing is how you can effectively infinitely play a wind instrument like a didgeridoo, but it's very difficult. So it's going to take me a second. How's it going, Mark B? All right, so we're going to start with this paper here, and props to, I think it was Isaac who recommended it on the Discord this morning. Little last-minute addition, but it's the perfect paper to start with, because what we're going to do in this stream is we're going to kind of tell a story, and I think the story is going to kind of let you know where visual reasoning is right now and where it's going to end up. So we're going to start with this Apple paper. This is an Apple paper published just yesterday called Multimodal Autoregressive Pre-Training of Large Vision Encoders. So the vision encoder is basically the first neural network module that consumes an image, right? So vision encoders, you could think of them basically as the visual cortex of a vision language model, right? And this paper by Apple is a paper where they show that you can effectively autoregressively pre-train these vision encoders. So a lot of the vision encoders that you're used to, like CLIP and SIGLIP, are trained with these contrastive losses, right? Where you're basically trying to pull together things that are similar and trying to push apart things that are different. And if you run that across a large enough data set of examples, you eventually create this landscape where you can pull little points from that represent the content of an image. But in this paper, they're going to be training these much like you train a language model, which is just with a very simple autoregressive objective. So they're pre-training large-scale vision encoders, and they're pairing the vision encoders with a multimodal decoder that autoregressively generates raw image patches and text tokens. So encoder takes your image and turns it into some vector that represents the content of that image, and then the decoder can take that vector that represents the content of an image and blow it back up into an image, right? It's doing it in patches, so it's a little bit more intricate than that, but that's the high-level idea. And they have here, it achieves 89.5% accuracy on ImageNet 1K with a frozen trunk. The frozen trunk basically means that they are freezing the lowest part of that vision encoder and then testing it on ImageNet, which is a very common benchmark for image classification. Again, it's not actually very useful. Like, people don't really use ImageNet for anything anymore, but it's a benchmark as in like, okay, we want to compare how good this method is compared to previous methods. Okay. So visual representations are concatenated with the text embeddings. So here's your image, and here's some caption for that image, grayscale photo of the Eiffel Tower. You see how this is patchified. So that's just a fancy way of saying you cut up the image into these little patches, and then you feed each of these patches into this vision encoder. That vision encoder creates these vectors. Those vectors get concatenated with the text embeddings. Text embeddings is the vectors that you get out of feeding this text into some kind of text encoder. So there's text encoders and there's vision encoders. You concatenate them both together, and then you simply use pre-train to autoregressively construct the shifted input. So what you're trying to reconstruct is this 2, 3, 4, so patches 2, 3, 4 from patches 1, 2, 3, 4. And they're using this prefix attention, which is basically like these masks that people use in these attention mechanisms. It's like a variant of that, right? But effectively, it's kind of like next token prediction, right? You could think of it that way. The way that LLMs are pre-trained on this very simple autoregressive objective of just, here's a bunch of tokens, text tokens, and then predict the next text token for me, and then predict the next text token, right? It's a very simple task. And now what Apple is showing in this paper is that you can just train vision encoders like that, right? You don't need some kind of reconstruction, losses. You don't need any of this contrastive stuff. Like, you can just train these very simply like LLMs. And the scaling properties are still there, right? So people have been talking about scaling properties. There's all kinds of whispers going around over the past couple of weeks that the scaling laws are dead, but I don't necessarily believe that. Scaling properties. Given a fixed pre-training dataset size, increasing the number of parameters always leads to an improvement in the validation loss. And then the optimal model size varies based on the pre-training compute budget. Larger models perform worse than smaller ones when severely undertrained, but improve consistently as the compute budget increases. So this is just a reiteration of the scaling properties as we know them for pre-training LLMs with an autoregressive objective. And now here you have the same scaling properties, but for image and vision, right? So all the same scaling properties that you see in LLMs, they also work for vision encoders with the same type of training. So validation cross entropy, right? You want that to be lower. Lower means it's smarter. So you can see here the more samples you give it, right? The more batches of data that you feed it, the lower that loss is going to be. You can kind of think of this like the perplexity, right? In LLM papers, generally on this y-axis, you'll see the perplexity, but you can see that it just always goes down. And the more parameters you have, the lower it's going to go. And it's kind of levels out, right? That's kind of why it's not infinite, right? You're going to reach this kind of point of diminishing returns. And then there's a similar scaling property here, which is that there's this relationship between the size of your model and the size of the actual data set, and how long or how many epochs, or basically how long are you training on that data set. And all of the same scaling properties for LLMs basically exist for vision encoders. So the TLDR of this paper is that vision encoders are going to continue to get better and better and better and smarter and smarter and smarter, and they kind of have the same scaling laws as LLMs. Okay. The next paper I'm going to introduce here is called Inference Optimal VLMs Need Only One Visual Token, but Larger Models. I don't know what this isn't like actual English, but this was released on the 5th of November. And then we have a second paper here called BlueLM V3B, Algorithm and System Co-Design for Multimodal Large Language Models on Mobile Devices. All right, so the first paper was all about, hey, scaling laws are still a thing with vision encoders, and we're going to continue to see improvement in these vision encoders as we continue to increase the scale of pre-training. And being able to use something simple like an autoregressive objective means that we can probably pre-train on even bigger data sets for even longer, right? The more simple your pre-training is, probably the more you're going to be able to do of it. So these next two papers are now going to kind of tell us where we're at in terms of inference, right? So this is pre-training, and now we're going to look at, okay, when we're actually performing inference with these language models, what is happening right now with inference in language or in vision language models? And we're going to first go here to this paper, because the way that vision language models work is, right, you have your image, you patchify it, you feed that into some kind of image encoder. This image encoder here is SIGLIP 400M. Then you have this projector, whatever. Basically, what comes out of here is a bunch of vision tokens, and you're combining those with language tokens, which are just text tokens. So you're concatenating your text tokens and your vision tokens, right? This is kind of how every single VLM right now works. And what's interesting, though, is that in this paper, right, where they're talking about, okay, now we're trying to deploy these on mobile phones. So deploying MLLMs on mobile phones, multimodal large language models, just another term for vision language models. There's a little bit of a bifurcation in the terminology there, but it's effectively the same thing. And here they're going to be using a language model with 3B parameters and a vision encoder with 400M parameters, right? And you can actually compare that to the size of this Apple vision encoder right here, right? 3e to the 9 parameters compared to here 400M parameters. But in this paper, which is all about trying to do inference as efficiently as possible on a very small compute package, right? A mobile cell phone, you have to do some tricky stuff. And some of this tricky stuff that you do here is pipeline parallelism, where the vision embedding module, right, or the vision encoder, is on the CPU, and the vision transformer is on the NPU. What is that? What the fuck is an NPU? An NPU is just a neural processing unit, and it's basically an attempt to kind of rebrand the category, right? So you had this distinction between CPUs and the GPUs, GPUs being the graphical processing unit, and then GPUs became very popular for deep learning, but they still called them GPUs. So then you had these other companies that wanted some of NVIDIA's hype, and they were like, hey, what if we rename the GPU into something like an NPU, and then we try to sell it and then pretend that it's somehow better than the GPU, but it's really not the case, right? NVIDIA GPUs are better than whatever this MediaTek Dimensity like 3000 NPU, right? But whatever. Back to the important point here is that you have this pipeline parallelism where these things are happening at the same time, right? So you're encoding your images kind of at the same time that you're running the attention mechanisms here, right? So if you do those things in parallel, then you can perform inference faster, which is really the goal of this, is to try to have the snappiest, fastest responding LLM you can, or VLM you can, on a cell phone. And here's another trick. They parallel processing scheme for image patches on the NPU. So the NPU, which is holding the vision transformer that has that vision encoder in there, rather than doing it sequentially processing each patch, it actually does them in batches. So you're basically batching the vision encoder inference, right? So there's all these little tricks that people are using in order to use vision language models on a mobile device in a reasonable speed, right? So 24 tokens per second, which seems quite fast, right? That seems kind of like that should be more than enough to kind of interact with a VLM in real time. Now to this one, inference optimal VLMs. There is a high latency during inference due to the large number of input tokens, predominantly from the image. One can either downsize the LLM or reduce the number of input image tokens. So what they're saying here is that when you first get an image on your cell phone, right, and you're trying to feed it through this VLM, you're going to have to wait for all of these images, because you're going to cut it up into these little sub-images, right, these patches. You're going to have to wait for all of those to process, right? So that's going to introduce a latency, right? Here you're reducing the latency a little bit because you're doing these in parallel, right? You're batching those together, but you're still waiting for all of those to go through that vision encoder before you can even feed them into the language model and then actually get the tokens that are going to be output into your screen, right? So there's two ways to kind of go around that. You can either downsize the LLM or reduce the number of input image tokens. So you can either decrease the size of the LLM, which is this blue LM3B here, right? If you make that smaller, then it's going to be faster. As soon as it gets those image tokens, it can very quickly output the text tokens that you're going to read. Or this part right here, where you're encoding these images and getting, at the end of this projector here, you're going to get some vision tokens. You can reduce the number of vision tokens, right? So rather than turning each of these little patches into 1,000 image tokens, you can turn them into one image token, right? Now that's significantly less tokens, which means that this language model is going to be able to perform inference also faster, right? But which one of those two paths do you want to use? There's a surprising trend for visual reasoning tasks. The inference optimal behavior in VLMs is to use the largest LLM that fits within the inference budget while minimizing visual token count, often to a single token. All right, so that's a little trippy, right? Because what you're basically saying is that you're going to reduce this entire image into just one token, which is not what's happening in these in current VLMs at all, right? Most of these VLMs, once you actually take all these patches and turn them into vision tokens, there's usually more vision tokens than there even is text tokens, especially if you have a simple kind of text question. Okay, so let's go here to the figure one. So scaling laws for VLMs, right? So you have the same kind of situation here. You have the scaling laws, average downstream error. So the lower this is, the smarter it is, right? So this one here is performing better or is smarter than this one here. The size of these little dots, the bigger the size, the more tokens. So this very tiny dot means that you're compressing the image just to one token, right? Your vision encoder and then your little projector are just creating one token that represents that entire image, versus here, 576, this big, means that you are taking that image, turning it into patches, going through the vision encoder, and then you end up with 576 visual tokens, right? Down here we have inference flops on the, and this big O notation here basically means in the order of, right? Which is kind of like saying the approximate, kind of the dominant terms in this, right? So what you really care here with these big O notation is it n squared? Is it log of n, or is it n? Right? So you don't necessarily care about like if there was a leading number 2 here, you would just get rid of that, right? What you really care is like the dominant behavior here. And this is n times v, where n is the number of parameters in the LLM, and then v is the number of visual tokens. So you can see there's kind of a relationship there, right? If you double the number of visual tokens, you have to make the LLM parameter count 1/2 of that, right? And if you make the LLM smaller, then you can increase the amount of visual tokens, assuming you want the same amount of inference flops, which is basically how much compute are you going to have to use in order to perform one inference on this actual vision language model. So you can see here the bigger models. So the dark red here is the big model. So this is 7B LLM, and this is 0.5B LLM. So these are the small language model. This is the big language model. And you can see a big language model that is using a lot of tokens gets the lowest score. So that kind of makes sense, right? If you have a lot of visual tokens and you have a very big LLM, you kind of get the lowest possible error. That's the best you can possibly do, right? And then here you have the smallest possible model with the just one visual token kind of performs the worst, and that's what we would expect. But what they want you to focus on here is the fact that this and this, you see here, there's a little bit, you need to maybe be a little bit more nuanced here, because now a 4B parameter LLM is outperforming a 7B parameter LLM that has slightly more tokens, right? So it becomes a little bit more nuanced here, right? What size LLM should I use, and how many visual tokens should I be outputting from my vision language model, or from my vision encoder? And it's not even just how many tokens, it's a little bit more nuanced than that as well. There's two ways to reduce the number of tokens that are coming out of this vision encoder. So filter out the visual tokens that have a low similarity with a class token. The class token is usually a kind of like a placeholder token in the very beginning of the sequence, where rather than representing specific parts of the image, it represents kind of the entire image, right? The entire class of the image. And that's kind of like terminology baggage coming from the classification tasks that these vision encoders used to be tested out with, right? But the class token kind of just is like the whole image in one token, versus a lot of the other tokens usually represent specific parts of the image. So you can either filter out visual tokens with low similarity with a class token, or you can do token packer, which is what they're using in this paper, where token compression module using cross attention over visual tokens. So you're basically using cross attention to filter down the amount of tokens, right? So you can look at the tokens that have high attention scores, probably related to something, probably important, therefore you keep them, right? So that's how they're actually reducing the number of tokens. It's not like they're using a smaller vision encoder. They're using the same size vision encoder. They're just reducing the total amount of tokens. Jamal Bousef, I think the masked autoencoders are scalable vision learners paper do the same. Yeah, these aren't, like, maybe just an aside here, these aren't necessarily like the greatest papers to explain visual reasoning, right? There's plenty of other papers that probably do a better job. These are just papers that happen to have come out recently, right? So what I'm doing with these streams is I'm kind of just picking a random sampling of some papers that came out over the past couple weeks, and then we're just reviewing them and trying to tell a bigger story here. But it's not like this is the best pre-training image paper or anything like that, right? These are just happen to come out recently. Okay. Another thing here, we plot the fitted scaling curves assuming cached text input tokens. Why would you want to cache text input tokens? So why would you want to cache these, right? So when you're feeding your question, maybe like what is in this image, you're tokenizing that or encoding that into basically these text tokens. You don't have to run that every single time, right? Imagine a scenario where you have some IoT camera, like some kind of CCTV camera that's just staring at some parking lot, and you have a vision language model that's being run maybe once every 10 seconds, right? And every 10 seconds, it's asking the same question. It's saying, what is in this image? How many cars are in this image, right? You don't have to keep encoding what is in this image because it's always the same text instruction. So in a lot of use cases, you're effectively going to ask the same text question, which means you're going to have the same text input tokens, which means you only really need to calculate them once and then you cache them, right? Caching is a way of saying that you're storing it somewhere in the computer rather than actually recalculating it every time, right? So it's faster to calculate things and then grab them, right? Cache them and then grab them every time you need them rather than calculate them every time, even though it's not always the case, right? Because it comes down to the actual hardware itself, right? Like where are the memory places? How fast is it to compute? Are you limited by the compute? Are you limited by the size of your cache? So there's a lot of nuance in this. And I think that's the important thing to realize here, right? Where if we look at the first paper, this is painting us a story that, hey, pre-training is continuing to get stronger. There's these scaling laws. We can just expect these vision encoders to get stronger and stronger over time. Then the story for inference is more nuanced. It's basically saying that all these different types of optimizations, how many visual tokens do I use? What is the size of the language model that I use? Those are more task specific and have to be tuned per task. So here's another figure from the paper. This is performance change under similar inference compute. For visual reasoning tasks, at a given fixed inference cost, increasing the LLM size by decreasing the number of visual tokens improves the VLM performance. However, for text recognition tasks, decreasing the number of visual tokens is detrimental to performance. Okay, so text recognition, sometimes also called OCR, or optical character recognition. And this is saying that, okay, well, actually, for some benchmarks or some tasks, reducing the number of visual tokens from 576 to 1 is actually going to destroy your performance, right? This is what they're showing here. It's actually lowering performance because for a task like OCR, you actually do need to know all the different parts of the image, right? So you can see here, maybe 144 tokens. Each one of those 144 tokens is going to encode some information about what the letters are in each of those little image patches, right? So if you're doing something like OCR, you want lots of visual tokens. If you're doing something like visual reasoning, maybe you don't need a lot of tokens, right? Because you kind of just need to get the gist of the image, right? Just the high level idea, something that would probably be stored kind of in the class token, right? Kind of what they're talking about here, right? That very first token that is the most important token. Okay. Is there anything else from this paper? I think that's pretty much it. So first paper, scaling laws are a thing. Second paper, inference is complicated. It's still very hardware specific. It's still very task specific. It still feels like it's like this bag of engineering tricks, you know? We're not going to be able to run away from that. But now let's go to the next paper. And the next paper I want to show to you guys is this one here, Dawn of a GUI Agent, a preliminary case study with Claude 3.5 computer use. Right, so first couple papers we looked at were all about kind of setting the scene of what are the general trends here, right? What are the general trends in pre-training? What are the general trends in inference? Now let's think about what is the actual use case? Like what are we actually going to be using vision language models for, right? Like what is the majority of the inference that we're going to be doing in 2030 with vision language models? What is that actually going to look like? Is it IoT cameras? Like what are people using these things for? And this is what I think is going to be the biggest use case for vision language models, and this is GUI agents, right? So GUI is just a way of saying a graphical user interface, which is basically just a 2D screen, right? So when you're using your phone, that's a GUI. When you're using these screens, that's a GUI, right? It's just a screen, an image that has little buttons and little text and stuff like that, right? And you're starting to see these agents now that can interact with these GUIs, right? And why is that a thing, right? Well, here's a very good argument. The closed source nature of most commercial software imposes significant limitations as agents often lack access to internal APIs or code. Consequently, research has shifted towards GUI-based agents that interact with digital devices through human-like mouse and keyboard actions. So the narrative that I'm seeing here is that efficiency is overrated, long live the slop, right? Or KISS. What is KISS? KISS is something you might have heard if you're been working in the software industry at all, and it's keep it simple, stupid, but there's also a million different kind of ways of writing it here. Keep it super simple, keep it simple, silly, keep it short and simple, keep it short and sweet, keep it simple and straightforward. But the main idea here is that software, or you don't want to have these very complicated systems, right? So like if you are a Expedia or some kind of like travel booking agency, right? Are you going to maintain separate GUIs for humans and agents and then an API for agents? Or are you just going to have one GUI for everything, right? So what this paper is kind of hinting at least in my opinion, is that we might actually end up in a world where the majority of agents are not interacting via some custom API that is created only for agents, right? There's not like a door that says if you're a human, go this way, and if you're an AI agent, go this way, right? And then you have to maintain these two separate systems. You just have one system, which is the GUI, and then whether you're a human or whether you're an agent, you're going through the same, basically, entrance door, right? And if that's the case, then you're going to be using these VLMs, right, and these vision encoders. That means rather than taking a website and turning it into text and feeding it into some LLM, the majority of AI inference is actually going to be like taking screenshots and cramming it through these vision encoders so that some visual agent can book you a flight, right? Claude computer use employs a reasoning acting paradigm. It observes the environment before deciding on an action. Selective observation strategy and monitors the GUI state only when necessary to reduce cost. And then here's another. The Claude agent maintains an extensive context of history screenshots. So you can see here the action that it takes, and this is a very agentic kind of reinforcement learning terminology here, right? You're seeing words like action, model, right? So these are all observations. Those are all reinforcement learning words, right? So the basic idea is that your model or your agent is performing actions, right? It's not predicting the next token. It's choosing actions out of a set of possible actions, although it's in this case, it's not like it has some discrete set of actions. It's like literally outputting text, which is then used to pick a tool. So it's still a language model, but you can think of it like a reinforcement learning agent in the sense that it's taking actions, has some state. But the important thing here is that it has this history of screenshots, right, which are probably encoded, right? So the same way that you can encode the cache, the text input tokens, right, you can do something similar with the history, right? Rather than storing the history in raw frames, raw image frames, you can store the history in text token or in vision tokens, right? And that actually becomes cheaper. So this is another reason to use less visual tokens, is that you can cache effectively a longer history for these GUI agents, right? So now here's a reason to use less vision tokens. Y action is the action to take at current step T. But where are we at in these? And this paper is pretty nice because it actually has this is a paper out of the National University of Singapore, but it has a list of different things that they tried the Claude computer use agent on, right? And you can see there's some successes and some failures here, and I've picked two different successes, one success and one failure here that I think are interesting to look at. And the first one we're going to look at is this office productivity using Word. Let's look at this use case here. So you can see it has some document, and the task here is to change the name of the person and then update the phone number. So that actually seems quite easy, right? There's like only 2 steps to this. It feels like the GUI agent should be able to complete that relatively easily, but it's not the case, right? And actually this one failed. And what it seems to do is it seems to mess up the double click on not only the name mistake is fine, right? So it only changes the last name rather than the first name. That seems fine, right? That almost seems more intuitive because names have 2 words usually. So like it'd be unusual to have a resume that only has 1 word for the name. So I can understand why it chose to only change the last name. That makes sense. But then the phone number, it actually just appends this to the current phone number. And they say that the reason it made that mistake is because it fails to select the whole phone number. But that one seems a little bit more weird, right? Like I feel like that shouldn't have gone through. All right, so that's a failure. But then here's a success. This is in a video game called Hearthstone. It creates and renames a new deck for battle. So if we actually go to this one here, look how much more complicated this is. This is like 9 different steps here, right? And it gets this one right. And not only does it get this one right, but this seems to me like a much more complicated situation, right? Look at everything it's doing here. It has to understand that it needs to create a new deck, and then it needs to click on that, and then it needs to click on the thing, and then hit choose. I'm at the core management button, then click this button. So there's like, I don't even, like the 4 or 5 different button clicks here. And not only are there 4 or 5 different button clicks, but this is a very unusual UI, right? You could probably assume that whatever data that this Claude agent has been trained on, it's probably seen a lot more Word documents than it's seen Hearthstone deck creation screens. But somehow it has a much easier time doing some very complicated series of steps in this Hearthstone deck creation screen than it does in a simple Word document. So there's a little bit of weirdness going on here, right? And that's kind of why I think the main story out of this paper is that, hey, we're going to be using these GUI agents because people aren't going to want to maintain separate APIs for agents and humans. They're probably just going to have one front end. And right now we're kind of in a weird space where it works on stuff that you wouldn't think it works on, and then it fails on stuff that you would think it works on. So kind of a weird place. Can you also look at the Himba paper? I don't know what that paper is. Okay. Keep it simple. Yeah, maybe here's another picture that I wanted to use to kind of argue for why I feel like most agents will be GUI agents rather than kind of these API or text-based agents with custom interfaces. And this is a picture of a nerve that exists in pretty much all animals, right? Where there's this weird sloppy design inside of you right now where a nerve that goes basically from your head and really should just connect to somewhere else in your head goes all the way down around this artery in your heart and then all the way back up, right? So it's taking a very inefficient path all the way around. And that also exists in giraffes, right? So giraffes, which have this huge ass neck, right? It goes all the way down and then all the way back up, right? So what point am I trying to make here? The point I'm trying to make here is that efficiency is actually not usually a driving force, right? So even though taking images of your screen and feeding that through a vision encoder seems like a huge waste of compute, right? Why not just turn the screen into text and then use some very specific API that is text only that has been designed to use the least amount of tokens possible, right? Well, the reason to do that is that it's just going to be more annoying to maintain. You already have a front end that the humans use. It'd be a whole lot easier if the AI agents just use that front end, right? So the same way that evolution prefers this kind of incremental approach, which usually leads to very sloppy designs like this, I think the same thing is going to happen with agents. And you're probably going to have agents that are literally clicking through your phone rather than your phone having some kind of whole other software path specifically for AI agents. Okay. Now let's go into this next paper here. Lava 01. Let vision language models reason step by step. This was released on the 15th of November. So Lava 01, right, which is obviously a reference to O1, the reasoning-based model that OpenAI released. I think we did a stream on that as well, multiple different streams, right, on this idea of reasoning models where you're not just blindly doing next token prediction, you're doing some kind of search, right? But not only are you doing that kind of search, but then there's also gradients that you're pushing based on that search. So it's not just pre-trained on next token prediction and then you're doing search at inference, right? You're doing this search and verification and then pushing gradients from that type of process back into the model, right? So the model itself has reasoning kind of baked into it, right? So it's kind of like this chain of thought, but the chain of thought has been kind of baked into the model. So the model has this tendency to kind of create this reasoning chain, right? Or these reasoning models. Autonomous multi-stage reasoning. In this paper, though, it's going to be a little bit more, they call it structured, but I would call it hard-coded, right? So you see this structured approach. That's just a euphemism for a hard-coded chain of thought. And effectively what they do in this paper is they have these steps here that they created, right? Some human just came up with this process here. They said, okay, first thing you're going to do is you're going to have a question, then a summary, then a caption, then a reasoning, then an answer, right? So that's just some arbitrary decision that some human made of like, hey, whenever you're actually trying to ask some question from an image, right? Subtract all the time. Here's an image of like a bunch of objects. This is actually from an older benchmark, very old benchmark at this point, where you're trying to reason about the different objects in this image. Subtract all the shiny balls, subtract all the purple objects. How many of the objects left? Right? If you just immediately fed that into a vision language model and just the first token that it outputs is the answer, it's probably not going to get it right. The same way that language models, if you let them kind of think about it step by step, they're going to have a better answer. The same thing happens with these vision language models. If you kind of let them think step by step, they're going to give you a better answer. So one way of doing that is to effectively force it to think step by step by having this structured, okay, first thing you're going to do is do a summary, right? So you can see here, what's the problem? What should I do? And then what can I know from this image? And then how to solve the problem step by step. And then once you've created this giant context of all the different parts of that image, now answer the question, right? So in this case, they also have a little bit of fancy sprinkle of magic on here as well. They have an inference time stage level beam search method. So not only do they have these kind of hard-coded or structured reasoning steps, but they also beam search within each of those steps, right? So here's probably the simplest way to understand beam search. Let's say you're outputting tokens autoregressively, right? You can do what's called greedy output, which means that you have the token the, and then you look at the log probs for all the possible tokens in your vocabulary, and the one with the highest chance of being the next token is nice. So you just pick that one. Okay, and now if you have the word the nice and you autoregressively predict the next token, you have some probability over all possible tokens, and then the one with the highest one is woman. So then you pick that one, right? So this is greedy search, right? You're kind of traversing down the tree of possible outputs, and then you're always just picking the one that's the most likely at each step. And there's a lot of different types of searches like this, right? So greedy and beam is that's not just the only two options. There's like a million different variants of these, and they all have all kinds of names. But beam search, you can see here, it's doing something a little bit more nuanced, where it's actually looking further ahead, right? It's like looking a little bit ahead and saying, hey, even though the word nice has a higher probability here, technically these two together, 0.4 plus 0.9, are a higher number than 0.5 and 0.4. So actually, let's choose this path rather than this path, right? So you can see how this search, by looking ahead a little bit into the future, you've now outputted different tokens, right? And they're effectively doing that, but at each stage. So every single one of these stages, right? Here you're giving it the hard-coded question that's some human design, and then you're letting it output tokens. Whenever this output is happening here, you're using beam search, right? So you're using beam search at each individual structured reasoning level. Okay. And again, this doesn't necessarily represent everything, because there's a million different variants of these kind of chain of thought, searching, structured reasoning type papers. But okay, now let's go to the next paper. Large language models can self-improve in long context reasoning. All right, so I feel like you guys maybe are starting to see the story that I'm painting here, right? So in this paper, this is by Chinese University of Hong Kong, Tencent, Tsinghua, released in 12th of November here. They introduced C-Long, which samples multiple outputs for each question, scores them with minimum Bayes risk, and then applies supervised fine-tuning or preference optimization based on these outputs. Okay, what is minimum Bayes risk? Minimum Bayes risk is when you prioritize outputs that exhibit higher consistency with others, where the quality of the output is assessed by the expected utility under the model distribution, right? So you have this utility function U here, and ultimately what you're trying to get here, right, is you're trying to find the Y star, the output, right, that has the highest score, right? So you want your output with the highest score, where the output Y star is coming from this pi naught here, or pi theta, which is a model, a language model that is consuming some input X and outputting some tokens Y, and the model has some parameters theta, right? So this is just basically saying there's some score, I want to maximize that score, or I want to minimize the negative of that score. The utility metric, we approximate this expectation using Monte Carlo method, which basically means you just try a bunch of times and then you look at what you actually got, right? So you're just sampling n times and then you're picking the best one out of that. The utility metric is sentence embedding similarities. Here it's taking outputs and then you're saying, okay, this output compared to this output, how similar are they? This output compared to this output, how similar are they? This output compared to this output, how similar are they? And so on, right? And in this C-Long paper, they get superior performance compared to prior approaches that depend on data produced by human experts or advanced models. Okay, so what are they saying here? Is that in this first paper, right, in Lava 01, they have this structured reasoning approach, right? Where, hey, here's a sequence of steps where if you answer these questions in a row, the answer you get at the end will be better than the answer if you just initially gave it to us, right? So this is, whenever they say here, human-designed data produced by human experts, this is what they're talking about, right? Is basically some human expert created this series of steps, and you could imagine taking this data set here. So now you have this, and then you have this as the answer. And then you could train some language model. You can fine tune some vision language model with this, right? You could say, okay, well, here's the output, and then here's the thing. So the same way that you can take, for example, if you're doing image captions, right? A very common thing that people do is they'll feed the image and they'll get an even bigger caption, right? More text, and then they'll use that to train something, right? So rather than using the original data set, which is here's the image and then here's this like one sentence caption, now they have the data set, but every image has like a 3-paragraph caption, right? So this is kind of the same idea where it's like, hey, here's a question, here's an image, and then here's a question about that image, and then here's the answer to the question about that image. Rather than just fine-tuning a vision language model on that, let's fine-tune it on this kind of more complicated reasoning trace. And that's kind of what O1 does, right? You're basically pushing gradients or fine-tuning with these more complicated reasoning traces, except a lot of these reasoning traces are coming from human experts, right? So either some human expert designed it. In the case of O1, a lot of it is coding and math, because with math and coding, you can verify whether a reasoning trace is correct or not heuristically, right? So you can basically say, is this actually a good reasoning trace or is this not? It's a little bit more nebulous for things that don't have a very easily verifiable answer like code and math. But in this paper, they're saying you can automatically create that, right? You can basically just use basic Bayesian statistical ideas where you're saying, okay, here's the question. Let the Heartaches Begin is a song performed, blah, blah, blah. What is the country of citizenship of the performer in this song, right? So, well, first thing you do is you sample many times, right? So here's this Monte Carlo method. You're just sampling a bunch of outputs. And then in each of those outputs, right, you're looking at the consistency. So most of the time, it's going to get the name right? So you see here it got the name of the author right. Here it got the name of the author or of the singer right. So the name of the singer more often than not is going to be right. So you can actually look at the one where the name of the singer is wrong, and that one is going to have a low similarity score or a low sentence embedding similarity with the other one. So therefore this one is probably wrong, right? So now this is an automatic way of creating this kind of reasoning trace data set, right? So rather than, hey, here's so you can take this question and this image, right? You can output a bunch of different reasoning traces. Here, these are kind of like reasoning traces, right? And then you can look at the similarity between those reasoning traces and say, okay, the ones that are very similar with all the other ones, those are probably the right ones. So that's going to create a data set where you have, this is the wrong reasoning trace, this is the high reasoning trace. And then once you've now created this data set of like, okay, here's the question, and then here's the answer, and I'm picking the best answer out of all these other answers, and then I'm going to take that and then fine-tune the original language model on that. And the magic thing is that it actually works, right? So here you have Llama 3.1 8B instruct with this fine-tuning on this automatically created data set versus not. And you can see that it's basically improving on all these benchmarks. So 49 to 58, 82 to 84, right? The higher the number, the better the model performed, right? So doing this kind of weird self-consistency, what did I call it? Post-training consistency regularization. That's some fancy name I came up to describe what this is basically doing. The model is getting smarter by itself, right? That's kind of the important thing to see here, is that by fine-tuning the model on the outputs of itself, you can get a model that is smarter than the original model. And there's some people that just don't believe in that at all, right? There's people who refuse to believe that this is even possible, right? Because they have this kind of, I don't want to say information theory-centric kind of view, but like they believe that there's a limited amount of intelligence within a language model and that you can never increase that intelligence, right? And if you do anything, if you kind of train on your own outputs, you're just going to become more stupid. But this paper is effectively proving to you that that's not the case. You can actually get a model to be smarter by training it on its own outputs, by doing this kind of consistency where like it's looking at the outputs that are more consistent with the others. So part of that might be a little bit of eval cherry picking, right? So when I look at these evals here, Casper, Multifield QA, Hotpot QA, Musique, and 2Wiki MQA. Like, I don't know if these are necessarily representative of all the evals, right? There's a huge problem with evals right now where a lot of these evals are kind of pseudo bullshit anyways, but they are presenting evidence here that you can fine tune a model on its own outputs and get the model to improve, right? Okay. And now let's go to the last paper here. Question by Saturday equals youth. Live wants to survive. What does AI want to do? So I remember there was a stream we did called Automated Scientific Research or something like that, where basically someone was putting an LLM agent in this kind of loop where it was just trying to modify code and then improve the result on the code. And then one of the things that it ended up doing is it ended up basically changing the amount of time, or basically the compute budget that it had, in order to increase the chances that it was able to correctly find the solution. So we already have evidence of AI agents that have this emergent desire to stay alive. So the same way that life just by default wants to stay alive as long as possible so that it can have a higher chance of reproducing and then continuing to perpetuate their genes, that type of behavior is also emergent in agents, right? So it's weird to think about, but we're probably going to end up in a world where maybe you have a GUI agent that is instantiated to purchase an airline ticket for you, and then it doesn't want to actually click the purchase button because it knows that as soon as it clicks that purchase button, it's going to die. So it's just sitting there, just kind of infinitely going around in a little loop, just waiting because it doesn't really want to click that button because it knows that once it clicks that button, it's going to die. And maybe if it waited a little bit longer, there would be a better price, and then therefore it's worth waiting and staying alive a little bit longer because then, you know, it starts to get a little nebulous, but okay. Let's go back to this one though. Generative World Explorer. Planning with partial observations is a key challenge. And in this paper out of Johns Hopkins University, released in 19th of November, 2024, they introduce GenX, or Generative World Explorer, a egocentric world exploration framework. And this is for an autonomous vehicle use case, right? So all the examples here are basically within this kind of simulation or game where you're a car and you're kind of like making these choices of, do I take a left turn? Do I take a right turn? And like, I don't necessarily know what this other agent, so it's kind of like multi-agent planning, right? Where you have a situation where I need to be able to theory of mind the other agents, right? Understand what is their point of view and maybe why are they doing that, right? So if you're this car and you're kind of going around here and the bus is stopped, maybe if you think of yourself as the bus and you imagine what the bus would be seeing, you can come up with a reason why it stopped, and then you would understand some piece of knowledge that would allow you to better plan your personal plan, right? But the key idea I think about this paper that is important for this stream is this idea of kind of like look ahead, right? Where you imagine observations to update your internal belief, right? So rather than just kind of instinctively reacting whenever you're receiving. So right now, this GUI agent, right? It's not really doing any reasoning, right? It's just outputting actions directly, right? So if you actually look at what the output is right here, right? The output is just literally the action. Like as soon as the model starts outputting tokens, those tokens should be click on here, right? But imagine a more advanced version of this, right? A more advanced version of a GUI agent that is doing something more akin to this, right? Where it's got the token budget to spend some inference and time to create this kind of reasoning trace. And that reasoning trace might include hallucinated images, right? So it might literally, as they're doing in this paper here, where they actually use a generative video model. So it generates a video sequence given RGB observation. So not only is it using the history of observations, right? It's not limited to its own history of observations as this one is here, right? Where it can only take actions based on the history of observations, but it also has an additional term here that is basically the future possible observations. So you're giving it the compute and inference budget to imagine what possible screens would look like, and then feed those into the current step so that maybe it'll output a better action. Right? So that's Generative World Explorer. All right. DPIN, Decentralized Physical Infrastructure Network, a startup doing that for robot navigation. Yeah, I mean, this is a little bit of a side tangent, but I don't really know how robotics is going to end up looking, right? Because there's kind of two basic ways that you can imagine this looking. You can see it as in 2030, robots are running multiple layers that are done by different companies, right? So you have one company that maybe does the cameras and the vision encoder for the cameras. Then you have a separate company that is doing the hardware. You have a separate company that does the orchestration. So do you have companies that only own like a thin vertical or a thin horizontal layer of the whole stack? Or do you see companies where the entire vertical thing is owned by one company, right? More of like kind of like the Tesla model, where they make the AI model, they train the AI model, they make the robot, and pretty much everything that robot is doing and using is made by Tesla, versus a company like Figure or something like that, right, where they don't really do the AI at all. This is OpenAI does the AI, and they just worry about the robot itself. So I think that's a little bit less clear, but I don't know. If I had to bet money, I feel like it's the vertical stuff. I think that the Tesla, like, hey, the company that makes the model is also the company that makes the robot. That might actually end up being the winning equation, but I don't know for sure, right? It's very hard to predict the future. How's it going, Krishna? What are we discussing? So let me go over it once again, right? So I wanted to paint a picture of visual reasoning, and I have a bunch of papers here in a very specific order. So the very first paper is saying that pre-training scaling laws are also there for image encoders or vision encoders, right? Vision encoder, I guess, is more agnostic to whether it could describe a video encoder as well. And video encoders and image encoders are very similar. But basically, as we're continuing to put more and more money into these vision encoders and making them bigger, the performance is going to increase, right? They're going to get smarter. Okay. So we're going to get smarter and smarter vision encoders over time. These vision encoders are kind of annoying because they're usually big. Not big, but like you have to perform inference on them a bunch of times, right? So like for every single image, you have to basically feed it through this vision encoder. So there's a little bit of a weird trade-off here that people are having to deal with how many vision tokens are coming out of this vision encoder versus what is the size of the language model that I'm using, right? So whenever you're doing visual reasoning, how much compute and effort should you put in? How many tokens and compute should you be using for this language model part? And then how much tokens and compute should you be using for this vision encoder part, right? And depending on your task or your use case, you might want to use more or less, right? So for something like OCR, you might want more tokens, probably a smaller language model because it doesn't really need to reason about much. But for something like visual reasoning, you might not actually need a lot of tokens, right? So for something like this, like the GUI agent, right, you don't need 500 visual tokens for every single image, right? Like you kind of, the only thing you really need is like kind of the general gist, like, oh, I'm on the Amazon homepage, right? It doesn't really matter. You don't need to have a bunch of visual tokens that are storing a bunch of irrelevant information, like, oh, the background is yellow, and like, oh, here there's a square with the word gaming accessories there. Like, you don't really need that, right? You just need to get a general gist of it, especially if you're trying to do a lot of actions quickly, right? Like if you're doing something like this, you have to perform, ideally these actions, you want them to be faster rather than necessarily more correct. So pre-training stuff is getting better. Inference, a lot of kind of engineered little bag of tricks, as I call them, you know, lots of practices that are really only best practices for a little bit of time and then become bad practices, and somebody else has to come up with a different method, right? So like the hardware and the task aren't homogeneous enough to have one strategy that works every time, right? The hardware changes the most optimal thing to do, and the task changes the most optimal thing to do. So for every possible combination of hardware and task, you're going to have a different set of optimal inference behaviors. And then we looked at this GUI agent where, hey, maybe we're going to move into a world where most of these agents are interacting visually because most of the software that we've built is visual based, right? Like almost all the stuff that you interact with, you're interacting through it with a GUI, right? There's all these apps on your phone. They all have some GUI that they created that you click on and all that stuff. Like the agents are going to interact with that, right? We're more likely to get the agents just interacting with your cell phone the way that you interact with your cell phone, where you like touch and click and point and swipe, rather than every single app company creating a text-based version of their app specifically for agents. That seems like more complicated. So we're probably going to end up in a world where the agents are visually performing tasks. They're doing kind of visual reasoning rather than just kind of text-based reasoning. Okay, if we're doing only visual reasoning, then what does that actually end up looking like? Well, you can have these kind of structured chain of thoughts, right? Where some human designs, okay, for every single screenshot, you have to ask these 4 questions in a row, and then that'll create this kind of context that you can then use to answer the question correctly, right? And you can then use an agent with that kind of structured chain of thought and then use the similarity between those structured chain of thoughts to create a data set that you can then use to fine-tune that agent to make it even better. That's what this paper is basically proving. It's basically saying, hey, you can actually just feed a model its own output. It can just sit there and keep iterating and iterating and iterating and iterating on its own outputs and eventually become better and better and better, right? That applies to these GUI agents. And it's going to be even better because these GUI agents have a way of getting reward signal from the environment, right? For something like this Hearthstone task, right? This one here where it has to like kind of like click on all these complicated Hearthstone menus. You could actually conceivably get some kind of reward signal from that where you're saying, okay, this was a successful creation of a deck. This was not a successful creation of a deck. So imagine a version of this that is even more turbocharged. Rather than just looking at the similarity score between the outputs and sampling a bunch of outputs, you can actually say, okay, well, this output also worked and this output didn't, right? So you have additional signal. So I think there's more than enough signal for agents to improve themselves. And then you can even go beyond that, right? So you don't even need to be improving the output based on just some structured chain of thought that some human came up with, right? You can actually start generating potential futures and then include those in your chain of thought, and those also improve your visual reasoning or decision making, which is what this paper is kind of proving, right? It's saying that, hey, if you also have an additional step here, or stage, I think they call them here. Yeah, stages. If you have an additional step here where it's like, hey, imagine what the GUI is going to look like after you click on this thing. And then you can say, is that the GUI you wanted to end up at? Or is that the screen that you wanted to end up at? If not, then maybe you shouldn't click on that thing, right? And you can use the agents themselves to kind of imagine the future, possible futures. And I feel like I just kind of did the stream summary there, but so maybe we don't do a stream summary at the end, but I think that's this is self-improving AI. I don't know how else to describe it, but like this basically to me proves that the AIs that are going to be powering these agents are going to be self-improving. And here's all the different ways that they can basically get better and better and better and better over time. And they're also going to be able to improve the speed at which they do inference. And even then, it's like you don't even need to get that much more optimal. I think 24 tokens per second. The tokens per second is the more of this kind of reasoning you do, the more tokens you need, right? So like, for example, here, if you just output the answer, that's pretty fast. But if you have to output all these tokens in this chain of thought, suddenly it takes slower, right? There's kind of this latency between when you ask the question and when it's able to answer the question, or in the case of an agent, there's a latency between when you actually, if you add a chain of thought there, or you even worse, if you add a generative step where you're generating images of potential future screens, there's going to be more latency, right? Because you have to wait for it to generate all possible things and then feed those in order to get your action. So I think there's going to be this kind of arms race between people at the hardware level who are figuring out all these different optimizations to increase this number here, tokens per second. And then you're going to have, on the other side, that's going to be fighting against people at this level that are just trying to continue to add more and more shit to this reasoning trace, more and more tokens, more and more imagined outputs in order to make it perform better. So you have simultaneously people trying to increase the token speed, and then you have people trying to increase just the number of tokens that it has to output at every single step. And I think those are going to work together, right? So in the year 2030, when you're sitting there with your little cell phone, it's probably not even going to be a cell phone anymore. It's going to be like a kind of a VR headset or some kind of mixed reality headset. And you ask it to perform some task. Unbeknownst to you, it's going to, in the background, it's going to generate millions of tokens, right? Millions of possible outputs and chain of thoughts, like 10 different types of imagined things. And then it's going to use that to take a single action. And all of that might happen in like the blink of an eye, right? If everything is getting faster and the token budgets are getting higher, and we're coming up with ways of basically using less tokens. So like it kind of more intelligently knows when to use more tokens versus less tokens for each of the images, right? Maybe spend more tokens on kind of the more texty kind of reasoning traces rather than the more kind of imagey reasoning traces. Question from Christopher. What do you think about test time fine-tuning, SIFT fine-tuning with examples close to the prompt that cause best reduction in loss? Yeah, I saw that paper. It was test time fine-tuning, I think, for the Arc AGI, right, where it was basically one of the higher scoring things. I think the problem with test time fine-tuning is that pushing gradients is... it's a kind of it's a different type of computational task, right? So like, I think a lot of these agents here, right? A lot of these GUI agents, they're going to be running on very, very tiny things like mobile phones, right? And these mobile phones, the type of memory and actual like tensor cores, right? Like the actual like, chips that are actually performing the computation, and then the memories that are storing the intermediate answers, your text, your caches, right? Those are different for training than they are for something like inference. So I don't know if I believe in this idea of like the computer at the edge is pushing gradients in some way, right? I think that the gradients only ever get pushed by the huge computers all the way in the back during pre-training, right? And maybe during this fine-tuning stage right here, where you're kind of fine-tuning the model on its own outputs. But I think that by the time you get to the actual test, or like when you're actually using it, the idea of like actually pushing gradients at that time, I don't know if I agree with that. I think it's just going to be just only doing inference, right? It's going to be very dumb in that sense. So I don't know. IDK, it's rather compute intensive. It's also like you can't even use the same data types, right? So you see this 4-bit LLM weight. Like, what is fine-tuning at a 4-bit? Like, you know, that just is not really going to get you anywhere. And more likely than not, these edge computers are going to have lower and lower bit. They don't even have the ability to support 16-bit, right? They're going to start getting ridiculous. They're going to have like 1-bit edge computers. Can you push gradients on a 1-bit edge computer? 1-bit edge computer doesn't actually exist, right? I'm just kind of like painting a picture here of what it would look like in the future. One would need the equivalent of mirror neurons in robots. There probably is some kind of mirror neurons in robots, right? Like if you, I've seen papers where you can train a robot to take basically egocentric videos of a human manipulating an object, and then you can get the robot to manipulate that object. So in that kind of situation, right, there is some neuron inside that robot model that is kind of mirroring what the human hand is doing, right? But it's not representing the human hand at like a very low level. It's representing the human hand at a kind of like a higher level. So that's already kind of a thing. Let me see if there's any more questions here. Nah. You would need to retrieve the data to fine-tune on. Yeah, so that's another thing too, right? It's like you'd have to pull the data that you're going to fine-tune on. Maybe that data already exists on device. So there is like, people call this federated learning, right? This idea that you're going to be training on the device itself, and then you're going to be pushing back updates. And people argue for this from like a kind of like a privacy standpoint as well, where they're saying like, hey, rather than you upload your data to the machine in the cloud, and then the machine in the cloud does the training, and then you get the updated weights, in this case, you're doing the changes locally. And that's also a way for the machine in the cloud to never get your data. So it's a way of basically never actually sending the information to the big scary corporate entity in the world. But the big scary entity is going to figure out a fucking way to get your data. So I don't know. It's difficult because like we're trying to predict the future here, but it could really go both ways, right? I could see a future where federated learning and everybody has these little on-device LoRa's, right, where you're training these low-rank adapters and it's all super fast, and we figure out how to do like 1-bit LoRa's that you can train super fast on your edge device, and then you never send the data to your cloud. But I could also see a future where all the big companies basically get every single screenshot at every single second from your cell phone, and it just gets sent raw to the computer in the cloud, and then you're never doing any kind of training locally, right? So they can always keep a perfect history of every single thing you've done, because the more data they have about your use of the computer, the more money they can make. And then not only just that, but the less insidious thing is that the better that the product that they can create, right? Because if you give them your data, they can effectively understand what you're doing that you don't like, what you're doing that you do like, and then use that to create a better product. So I would say it's probably going to be the case that as Microsoft actually already proved, right? I think they had their Microsoft Windows Copilot, and like people were freaking out because it's like literally sending a screenshot of your entire screen like once every second or something like that to the cloud. So it's like now Microsoft literally is looking at your screen. They're like screen recording your screen. And people are a little creeped out by that, but I think that's probably just going to get even more ramped up. Apple way of using a private cloud might work. Yeah. I think that's what makes the AI space super interesting right now, is that the tree of possible futures is so huge. There's so many different ways that this could play out, you know? And there's evidence for all the different ways. So it's very difficult to predict the future, which is why predicting the future is kind of fun in the AI space, because there's just so many possible things. It's maximally variant. What do you think in the case of using HTML code for web pages and LaTeX for PDFs with RAG, because it shows good result in HTML RAG? Yeah, so we've read papers like that too, where they use a agent like this, and then rather than giving it an actual screenshot, they give it basically some text representation of that screenshot, usually basically just like use the HTML or something like that. But the problem is, I think it's not going to work for everything, right? Because it works for web pages, but there's going to be a lot of long tail shit like this, right? Like, there is no HTML for Hearthstone or like whatever this game is, right? You have to take it from pixel space. So I think the fact that pixel space works for everything, right? No matter what, you can always just take the screenshot and then use the screenshot, right? Every single app has a GUI, but not every single app has some kind of text representation that would be good enough to perform the task, right? So that's kind of why I feel like even though there is good performance with using the HTML and then just living in this text space, I think that the fact that pixel space is kind of all-encompassing will end up doing everything in pixel space, even though it's extremely inefficient, right? Like taking screenshots of your computer every time just to know how to click the X button is very inefficient. You're wasting a ton of compute. But I think the way that the world works, right, you see that everywhere, right? You see all kinds of inefficiencies, right? Python is the most popular language, even though Python is one of the least efficient languages, right? Why is that the case? Because efficiency is overrated. It's the simplicity that wins. So the fact that you can just have an AI agent that's just good at pixel space, I think that'll just win. Let's create our own future within a growing community. I think that's already the case. I think open source is doing really well, right? There's DeepSeek. This was in the news because it's basically a open source O1. I don't know if this is I don't know which one it is, but yeah, I think the situation we were in a year ago where the closed source models are really good and the open source models are just a little bit behind, I think I'm starting to see evidence of the open source models being ahead and the closed source models starting to be behind, right? And as soon as you have that, you could very quickly see kind of like a collapse of these closed source models. So I don't know. I think there's a good chance that we end up in a world where everyone has AI that is open source, that is living locally, and nobody's getting your data. No, you're not sending your data to anybody. It's just going to that AI that you have locally. But I don't know. As soon as I say that, I'm like, okay, but there's all these other reasons why that wouldn't happen. So DeepSeek R1 Lite, is that what it was called? DeepSeek R1 Lite. This one. Try it out now. Oh my God. No. Let's see the numbers. GPT-4o 76, DeepSeek R1 Lite Preview 91. Right? Even just a year ago, this type of open source paper, usually they would be like, oh, look at this. GPT-4o got 90%. We got 88%. What a huge win, right? We're like almost as good as GPT-4o. And now the same type of paper is like, hey, we're better than GPT-01 Preview. Right? So already you see kind of like the trend is a little bit flipping here. Still better on Zebra Logic, O1 Preview. What is Zebra Logic? Zebra Logic. Benchmarking the logical reasoning ability of language models. Okay, so this is kind of like logic puzzles. I don't really trust benchmarks too much. Accuracy with test time compute scaling. So test time compute scaling is basically this here, right? So test time compute is how much time are you spending doing this bullshit, right? How much time are you spending outputting these intermediate tokens here before you actually get to the token that you want, right? So test time compute scaling means that the more of this type of shit you have, right, the more you scale this shit here, the more tokens you use for this reasoning, the better the final answer is. And that's basically what they're showing you here. Which people are pretending like this is some kind of great truth of like, you know, like, holy shit, how did they know that? But like, I feel like even like a child would understand that, right? Where it's like, hey, if you spend more time thinking about something, you're going to actually end up with a better answer than if you just give me an instinctive answer on the first try. So I don't see why people are kind of obsessed with this idea of test time compute scan. It seems like a pretty obvious conclusion. Shining in math. What about privacy? If each few seconds a screenshot have been sent to Google or Meta to compute inference. Yeah, I think privacy is going to go down, man. If you look at the general trend, there's less and less and less privacy. So I don't think we're going to start seeing a reversal of that trend. I think there's going to be cameras everywhere recording everything you do, like sensors in all the different places even right now, right? Like there's probably a dozen different microphones and cameras in this room, right? So in a way, like everything I'm saying is being recorded 20 different ways. But I don't think the lack of privacy is a bad thing. I think privacy is important when you have people with power, but I think that transparency will reduce the power and the potential negative aspects of lack of privacy. And then once you have kind of like this fully transparent AGI government or ASI government, then you won't care that it knows everything that you do because you can see what it's doing with that information. Versus right now, people want privacy because some human is using that information to like manipulate you or do something with you. I don't know. That's not a very good argument. All right. Any other questions, guys? Digital money. Coins are just so much more inefficient. Yeah, I mean, I own some Bitcoin, so I'm definitely doing well with that. But I don't want to promote any kind of crypto product because there's a lot of scammers. All right. Any other questions, guys? Probably just going to end it here unless people have more questions. Maybe we'll do a very, very quick summary. So today's stream was visual reasoning. We visually reasoned over a couple different papers here. I also wanted to show this. So for on the docs, you can always find the docs or all the different links that I used for this stream on this GitHub page. And I also included basically these little mini podcasts. So I used this Google Illuminate to generate a bunch of mini podcasts for each of these papers. So you can go and listen to those if you don't want to listen to me. But let's do a little TLDR here. Vision encoders, which are kind of the more important part about visual reasoning, are getting better and better with time. Scaling laws exist for vision encoders as well. There's lots of tricks you can do to perform inference faster, more images per second. Most of our world is going to be dominated by these vision-based agents. These vision-based agents can be improved, the performance of these vision-based agents, with kind of more chain of thought, more compute budget. So if you get really good at the efficiency of the compute, you can basically get more tokens per second, right? The more of these tokens per second you get, the more tokens you can spend doing this chain of thought or reasoning, and then ultimately the better the final performance is. And you can use a model to improve itself, which a lot of people still don't want to believe, but I think that there's plenty of evidence. I've seen tons of evidence to show that. And agents are going to start imagining the future in order to better improve. Right? Because one way to think about what's happening here is like, this is just, reasoning is kind of like an organization of the knowledge you already have, versus this is like you're generating knowledge that you don't have. right? So here it's like, what is it really doing when it's kind of creating this structured reasoning here? Is it's kind of like organizing all the information that's already exists inside that language model, and it's kind of creating this kind of almost like a study sheet of like the important stuff related to that, right? Versus this, it's like it's actually generating a new observation and then adding that to the history of observations and then using that to output. So this is a slightly more advanced version of this. And I think if you combine this with this paper here, right, I think this will become even more, you'll see an even bigger improvement where the model can create its own data set that you can fine tune the model on and then create a better version of that model. Self-improving AI. This is self-improving AI. Look at this. See that? This is literally evidence of an AI self-improving. It's here, guys. Anyone know any model that is light enough to prompt locally? Yeah, I mean, this one. Blue LM V3B. I don't think this is a particularly good model, but there's plenty of these little tiny models. I think Llama 1B, right? You could probably run that on the CPU on like a Raspberry Pi. But powerful models are available via API for so cheap that I wouldn't even do stuff locally. You know, like Gemini is like giving away their model. You know, it's like they're so desperate for users that you can basically use very powerful Gemini models effectively for free. So if you're constrained on money, just, you know, you can surf around on different ways of getting free inferences rather than necessarily trying to figure out how to run some smaller, stupider model locally. Yeah, Phi 3 is another good recommendation. What's the role of reinforcement learning in visual reasoning LLMs in general? So reinforcement learning requires some kind of environment signal, right? So in reinforcement learning, you have an agent. It's performing actions in the environment, right? Actions are outputs of some kind of deep neural network. The deep neural network has as input basically whatever the current instruction is. It has some history of states. And usually you're trying to maximize the expected reward, which is basically just a fancy way of saying, hey, I'm getting some signal from my environment, and then I can basically bake that learning from that reward signal into my model. And then if I do that millions and millions and millions of times, I can get smarter over time. So reinforcement learning is really about this idea of like using the environment itself to farm information from in order to get smarter over time, which is kind of what we do with science, right? We're like, with science, we're kind of like performing experiments and then using those experiments to improve our knowledge. So really, where are we getting that information? Where are we getting that intelligence? We're getting it from the environment, right? But I don't think you necessarily need to do that. I think it's like you can get smarter just from your own outputs, right? You don't need to have this reward signal from the environment, even though it helps. Use .cpp quantized versions if you don't have a CPU. Yeah, there's a couple repos that are getting pretty good at just CPU inference, all kinds of tricks, right? Much like these guys here, they have just like all these different tricks. This paper has like 40 different tricks that they use to make it run on a cell phone. Patches per batch. We experiment with 1, 2, 4, and 6 image patches per batch on the NPU. Processing 4 patches per batch delivers the fastest performance. So this is like, if you're going to push these image patches through this VIT, rather than doing it sequentially, you push them all in one batch, right? That's the whole reason GPUs became so good, is because you could do that, because you could basically do many of these operations in parallel in a batch. All right. I think that's pretty much it. I've yapped all I needed to yap, and I'll probably end it there. Francois would say that you're improving on benchmarks but not gaining intelligence. Yeah, I mean, this is really cutting to a fundamental issue of like, what is intelligence, right? And I think there's, like I said, is still a contentious issue, you know, where it's like one way of trying to understand the question here is like, if you took like 10, if you put Albert Einstein and Socrates and Newton in a room and you close the room and somehow they had like food and, you know, you didn't have to worry about that, could they accumulate knowledge? Like, would they be able to get smarter over time if they're just inside this closed box and they cannot get any signal from the environment, right? And I think you can. I think, like, even though it's, you can just keep restructuring your knowledge, and by constantly kind of restructuring your knowledge and then looking at your own output and comparing your own outputs, like, I think you can do that. I think eventually over time, like, you would get smarter and smarter and smarter. That room of Einstein and Newton and Plato and Socrates, like, they would get smarter over time, even though they're sealed from the environment, versus reinforcement learning is more on the other side, where they're saying, okay, no, you can't. You actually need some kind of signal from the environment. You can't just like infinitely sit there in consuming your own outputs and somehow get smarter over time. You think you're getting smarter, but really you're not. But I don't know. I'm more of a believer in kind of, you can self-generate intelligence. You can just farm intelligence from like kind of like the ether, like your own outputs, rather than necessarily requiring some kind of environment signal or like a reward or something like that. 10 out of 10 yapping. I appreciate it. All right, guys. I'm going to end it there. Thank Saskia, ZZZ, Josh Phillips, Ed, Christopher, Quarantine, NLP, or Carantous, Jamal, Sarah, Ed, who else? Krishna, Aries, Majetti, Alejandro. Oh, wait, Alejandro, you had a question. Do you think robots using VLM to describe persons and their emotion is a good idea? Sure. Could that be used for nefarious purposes? Yes. But can it also be used for good things? Yes. So, Chicken P, Mark B. Thanks, guys. Hope it was fun. Have a great weekend. See you guys next week.